Hello, Assalamu alaikum. Today we want to talk about Chapter 10, Part 1, Gases. In many ways, gases are the most easily understood form of matter. Even though different gaseous substances may have very different chemical properties, they behave quite similarly as far as their physical properties are concerned. For example, in the atmosphere we live is composed of a mixture of gases we refer to as air, a mixture of mainly N2, 78%, oxygen 21%, with small amounts of several other gases including argon 0.9%. Now, of the few elements that exist as gases at ordinary temperatures and pressures, helium, neon, argon, krypton, and xenon are monoatomic, and H2 and 2O2, F2, and Cl2 are diatomic. Many molecular compounds are gases. Note that all of these gases are composed entirely of non-metallic elements, which means they have low molar masses. Now, gases differ significantly from solids and liquids in several aspects. For example, they expand to fill their containers. They are highly compressible, forming homogeneous mixtures like the air we talked about, and they have extremely low densities. They have extremely low densities. In any given volume of air, for example, the molecules take up only about 0.1% of the total volume, with the rest being empty space. Thus, each molecule behaves largely as though the others were not present. As a result, different gases behave similarly, even though they are made up of different molecules. Now let's talk about pressure. Now, in everyday terms, pressure conveys the idea of force, a push that tends to move something in a given direction. Pressure P is defined in science as the force F that acts on a given area A. So P equal F divided by A. Gases exert a pressure on any surface with which they are in contact. Atmospheric pressure. Now, the atmospheric pressure defined as the force exerted by the atmosphere on a given surface area, and we can calculate this atmospheric pressure. Suppose you have a column of air that has a mass of 10,000 kilogram and has a diameter of 1 square meter column of air, and طبعا the gravitational force of 1 atmospheric pressure at surface. So atmospheric pressure is the weight of air per unit of area. Now we calculate the magnitude of this atmospheric pressure as follows. Now, the force F exerted by any object is the product of its mass m and its acceleration a. So F equal m times a. The acceleration is given by Earth's gravitational force to any object located near Earth's surface is 9.8 meter per second square. Now imagine a column of air 1 meter square in cross section extending through the entire atmosphere as the one in the previous page. That column has a mass of roughly 10,000 kilogram. Now the downward gravitational force exerted on this column is F. Is F equal ma. This is the mass, this is the acceleration. So we get this answer 1 times 10 to the 5 Newton. Now where Newton is the abbreviation of Newton is the SI unit for force. 1 Newton equal 1 kilogram meter per second square. Now the pressure equal force divided by area. So we have this is the force divided by 1 meter square, and this equal 1 times 10 to the 5 Newton per meter square. And this will equal 1 times 10 to the 5 Pascal, which is equal to 100 kilopascal. Now, the SI unit for pressure is the Pascal. Remember that 1 Pascal equal 1 Newton per meter square. Thus, the atmospheric pressure at sea level we just calculated is 100 kilopascal, can be reported as 1 bar. 1 bar equal 10 to the 5 Pascal and equal 10 to the 5 Newton per square meter. Another pressure unit is pounds per square inch at sea level. However, atmospheric pressure is 14.7 pound psi or pound per square inch. Now, what are the units of pressure? Millimeter mercury or torr. These units are literally the difference in the heights measured in millimeter, each of two connected columns of mercury. Remember, this is a mercury barometer. Here we had a vacuum, and then here this is the pressure exerted by mercury column on the surface, on mercury surface. And here we have the atmospheric pressure that is exerted on this mercury also. Now, this is called the Torricelli experiment. Torricelli, he invented this barometer, as I explained. When the tube is inverted into the dish, some of the mercury flows out of the tube, but a column of mercury remains in the tube. Now, Torricelli argued that the mercury surface in the dish experiences the full force of Earth's atmosphere, which pushes the mercury up the tube until the pressure exerted by the mercury column downward due to gravity equals the atmospheric pressure at the base of the tube. Therefore, the height h, this height h of the mercury column is a measure of the atmospheric pressure and changes as atmospheric pressure changes. So atmosphere, 1 atmosphere equals 760 torr. Also, we have the so-called standard atmospheric pressure, which corresponds to the typical pressure at sea level, is the pressure sufficient to support a column of mercury 760 millimeter high. In the SI units, this pressure is 101.325 kilopascal. Standard atmospheric pressure defines some common non-SI units used to express gas pressure, such as the atmosphere. Now, and the millimeter of mercury. The later unit is also called the torr. Then we have normal atmosphere at sea level is referred to as standard pressure. It's equal to either 1 atmosphere 760 torr, which is equal to 760 millimeter mercury, and also equal to this 101.325 kilopascal. We will usually express gas pressure in atmosphere, pascal, kilopascal, or torr as we go in this. Now, we use various devices to measure the pressures of enclosed gases. مثلا tire gauges, for example, measure the pressure of air in automobile and bicycle tires. In laboratories, we sometimes use a manometer, which operates on a principle similar to that of a barometer. So, using a manometer to measure gas pressure, this device is used to measure the difference in pressure between atmospheric pressure and that of a gas in a vessel. And notice that here the pressure of the gas is greater than the atmospheric pressure, and it's equal atmospheric pressure plus the difference in the height of the mercury in the U tube. Now we can look at this sample exercise using a manometer to measure gas pressure. You have on a certain day the barometer in the lab indicates that the atmospheric pressure is this number. A sample of gas is placed in a flask like this to an open-end manometer. A meter stick is used to measure the height of the mercury above the bottom. The level of mercury in the open-end arm is 136.4 millimeter, and the mercury in the arm that is in contact with the gas, this height, 103.8. What is the pressure of the gas? In two ways, in atmosphere and in kilopascal. So we are given the atmospheric pressure, this, and the heights of the mercury in the two arms of the manometer. We ask to determine the gas pressure in flask. We know that this pressure must be greater than atmospheric pressure because manometer level on the flask side is lower than that on the side open to the atmosphere, as indicated. So again, a mercury manometer. This device is sometimes employed in the laboratory to measure gas pressures near atmospheric pressure. So here, to solve, what is the pressure of the gas equals the atmospheric pressure plus H. So we add them together. H is the difference between the two heights. So after that, we convert the pressure of the gas to atmosphere, as you can see here. And this is the answer. And then to calculate the pressure in kilopascal, we employ the conversion factor between atmosphere and kilopascal, which is this, and we get the answer. Using a manometer to measure the gas pressure. Okay, we solve that. Now, the gas laws. Now, 4 variables are needed to define the physical condition or state of a gas: temperature, pressure, volume, and amount of gas, usually expressed as number of moles. The equations that express the relationships among these 4 variables are known as the gas laws. Because volume is easily measured, the first gas laws to be studied express the effect of one of the variables on volume, with the remaining 2 variables held constant. Then here we have the so-called Boyle's law, or the pressure-volume relationship. Now, it states the following: the volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure. So here in this, this is Boyle's experiment relating pressure and volume of a gas. Here we have, he placed 60 ml of a gas in the closed end of this U-tube, and of course it is because of atmospheric pressure. We have this, the 2 arms are equal. Then what he did, he doubles the atmospheric pressure by adding another 760 millimeter mercury, and he noticed that the volume of the gas decreased into half. So doubling the pressure caused the gas volume to decrease to half its original value. And this is the same as we say gas volume increases as the pressure exerted on the gas decreases. Now this explains why, مثلا, a balloon, as a balloon rises in the atmosphere, its volume increases because the pressure decreases. Now, if you, as P and V are inversely proportional, a plot of V versus P, as you can see here, is a curve. Since PV equal K, V equal K times 1 over P. Now this means a plot of V now versus 1 over P will be a straight line, as you can see here. So this is a straight line. As long as temperature and N are fixed. So for this is Boyle's law. For a fixed quantity of a gas at constant temperature, the volume of the gas is inversely proportional to its pressure. Now, the TV relationship, the so-called Charles law. If we have a balloon that is inflated, if we expose it to heat, the volume will increase. And if we expose it to decrease in temperature, then the volume decreases. And here we conclude that volume of the gas is directly proportional to the absolute temperature. In this case, pressure and N are fixed. So when we plot volume versus temperature, as you can see here, we get this straight line. If we extrapolate it here, it reaches here. Now, the volume of a fixed amount of a gas at constant pressure is directly proportional to its absolute temperature. Now, notice that here, the extrapolation here cuts the x-axis here at, the temperature scale at this value, minus 273. And this corresponds to 0 volume. But the gas, this condition is never realized. However, why? Because all gases liquefy or solidify before reaching this temperature. Now, William Thomson, a British physicist whose title was Lord Kelvin, proposed an absolute temperature scale now known as the Kelvin scale. On this scale, 0K, called absolute zero, equal this value, minus 273.15 degrees centigrade. So, in terms of the Kelvin scale, Charles' law states the volume of a fixed amount of gas maintained at constant pressure is directly proportional to its absolute temperature. So, doubling the absolute temperature causes the gas volume to double. So, mathematically, we can say, V divided by T equal K, or constant. طبعا with the value of the constant depending on the pressure and on the amount of gas. So the volume again, a plot of V versus T will be a straight line. We explained that. Now, the quantity-volume relationship, the so-called Avogadro's law. Now, Gay-Lussac observed the law of combining volumes. The volume of a gas at constant temperature and pressure is directly proportional to the number of the moles of the gas. At a given pressure and temperature, the volume of gases that react with one another are in the ratios of small whole numbers. And here we can say 2 volumes of hydrogen react with 1 volume of oxygen to produce 2 volumes of water vapor. Mathematically, this means V equal constant times N. Now, the ideal gas equation. Now, all 3 laws we just examined were obtained by holding 2 of the 4 variables, P, V, T, and N constant, and seeing how the remaining 2 variables affect each other. We can express each law as a proportionality relationship. As you can see here, volume is directly proportional with 1 over V, Paul's law. Volume is directly proportional to T, Charles' law. Volume is proportional to N, Avogadro's law. Then we can, combining these, we get into a general gas law. V is directly proportional N times D divided by P. Okay, again. So then becomes R here. We put a proportionality constant R, then we obtain this, and PV equal in RT, which is the ideal gas equation, also called the ideal gas law. An ideal gas is a hypothetical gas whose pressure, volume, and temperature relationships are described completely by the ideal gas equation, as you can see here. The term R is the ideal gas equation. The ideal gas equation is the gas constant R. The value and units of R depend on the units of P, V, N, and T. The value for T in the ideal gas equation must always be the absolute temperature, N in moles, pressure in atmosphere, and volume in liters. So this table shows the numerical value for R in various units. Then, numerical values of the gas constant R in various units. As you can see here, we have all these. Joule per mole times K. This is an SI unit, as well as this cubic meter Pascal per mole K. Also, this is another SI unit. Okay, now we want to define this condition, the standard temperature and pressure. The condition 0 degrees centigrade and 1 atmosphere are referred to as standard temperature and pressure, STP. The molar volume of an ideal gas at STP is equal to this value, 22.41. This is also known as the molar volume of an ideal gas. The molar volume of an ideal gas. We can look at this sample exercise using the ideal gas equation, how to calculate or how to use it in calculations. Calcium carbonate decomposes upon heating to give CaO solid and CO2 gas. A sample of CO is decomposed and the carbon is collected in 250 ml flask After the decom is complete, the gas has a pressure of 1.3 atmosphere at a temperature of 31 degrees centigrade. How many moles of CO2 gas were generated? So here we have the volume, we convert it to liter, we have the pressure, we have the temperature, we convert to Cada, then we calculate N from the ideal gas equation, N equal PV divided by RT, and this is the value of N. N equal 0.013 moles of CO2. This is the number of moles that were generated. Now relating the ideal gas equation and the gas laws. Now the gas laws we discussed in section 10.3 are special cases of the ideal gas equation. For example, when N and T are held constant, the product nRT contains three constants, and so must itself be a constant. PV equal nRT constant or PV constant. We can use Paul's law to determine how the volume of a gas changes when its pressure changes. P1 V1 initial values equal P2 V2 final values. So we can calculate the volume to the final volume if we know the final pressure, we know the initial pressure and the initial volume. In a similar way, we can start with the ideal gas equation and derive relationships between any other two variables, V and T Charles' law, N and V Avogadro's law, or P and T. So let's look at this sample exercise, calculating the effect of temperature changes on pressure. Here, the gas pressure in an aerosol can is 1.5 atmosphere at 25 degrees centigrade. If the gas inside obeys the ideal gas equation, what would be the pressure if the can were heated to this amount? You make a small table like this. Pressure and temperature, the initial values are given. You see, 25 and 1.5, you convert it to absolute. The final P2, we want the final. At this temperature, we add this to 273, we get this value, and we apply. So we have this P1 divided by T1 equal P2 divided by T2, and then we can calculate P2 as you can see in this case. P2 is 3.6 atmosphere. This answer is initiatively reasonable. Increasing the temperature of a gas increases its pressure. End of part 1. Thank you.